Let's look in detail at the life of a blue star. After only 1 million years or so, the hydrogen in the core is used up. The reaction stops and the star collapses, heating up both the core and the gas envelope. Under compression, hydrogen gas in the envelope starts fusing. It heats and expands to form a supergiant. The really big ones become white giants. The somewhat smaller ones end up red. In the core, compression produces enough heat for helium to fuse to carbon and oxygen. Taking 1 million years to complete, this is the first of a sequence of increasingly rapid fusion reactions that produce a series of elements. Each time a fusion reaction in the core runs out of fuel, the star collapses under the force of gravity. With each collapse, the core gets hotter, until the next reaction is triggered and the star undergoes massive expansion. When the temperature reaches a blistering 3 billion degrees, it takes only a few days for iron to form from silicon and sulfur. Iron itself cannot fuse spontaneously to become anything else. As the star goes from one reaction to another, it heats up and cools down, so its position on the HR diagram moves back and forth across the top. Eventually, no more heat comes from the core. The star collapses, falling at incredible speeds, up to 1/3 the speed of light. The core temperature soars, reaching an unimaginable 100 billion degrees. The remaining hydrogen and other fuels fuse together in one last massive meltdown. A supernova, a colossal explosion, and the biggest light show we will ever see. It's over in an instant, but it's bright enough to outshine an entire galaxy. Coming out of this chaos are the newly made heavy atoms, such as iodine, lead, gold, and uranium. Only a supernova explosion can generate enough energy to make those elements that are heavier than iron. In time, matter ejected from supernova explosions will mix with gas clouds and condense back into the stuff of which everything in our galaxy is made: the stars, planets, and even people. As the Earth contains many elements heavier than iron, we must all be children of a supernova. For all their spectacle, most supernovae leave a faint and very modest memorial, a neutron star only a few kilometers across. And the bigger they are, the further they fall. Some of the supernovae compress even further to become the ultimate cosmic has-been, a black hole. The gravity from a black hole is so great that not even light can escape, so it appears black. We can only detect them because of the massive X-rays given off by matter as it falls in. No one knows what is beyond a black hole, which makes it such a hot topic for science fiction writers. What's on the other side? Another Big Bang? Another universe with different laws of physics? Ever since the beginning of time, we have looked to the stars and wondered about their origins, little knowing that we have much in common. Through analysing starlight, we can work out what goes on inside them and what their future may be. And we now know we're all made of the same stuff: stardust.